from A, we try to represent the linear transformation represented by the matrix A. We want to project it in a new basis. The new basis, it will be composed of the eigenvectors of A. Okay, so this is how the procedure is. For the matrix A, we find A minus lambda I. Okay, so this is the first step that we determine. Then we write down, we want the determinant of A minus lambda I gives to us a characteristic polynomial. Then from here, we find the eigenvalues, the lambda I, and from lambda I, we can find the eigenvectors Vi, and the Vi, they constitute the matrix P, which helps to do the linear transformation from the standard basis to a new basis. And now, the standard basis, we can assume that this is the standard basis. This is the new basis, which is composed of the vectors V1, V2, Vn. Okay, this is the basis. And here, we move using the matrix P from the new basis to the standard one. Here, we have the matrix A. Here, we have the diagonal matrix D. And then, for any vector which we can find here, such as x, here, the vector is going to be u. And the x as a vector, this is equal to, it is seen from the graph, okay? So we apply this linear operator, or the matrix P, we apply onto u. So this would be equal to P times u. And similarly, any vector which is, here we can have x1, this can be u1. Again, we can say that u1 is equal to P inverse times x1, okay? So we can use, so going from one domain to the other, this is how we move across. And then we also know that the diagonal P, this was equal to P inverse times A times P, times the matrix P. And regarding this step, do you have any comment? Okay, now here is a sunny day. It's good for us. Is it better? Ashtomir, un comentou pак? Okay, okay, so let's move on. So this is the matrix D, which is diagonalization of A, and at this stage, what we can do is that we can multiply both sides of the equation by a P matrix, okay, and we get the following, and then we know that the matrix multiplication, we can do the P times P inverse, and this will be equal to the identity matrix. So here we can say that PD, this is equal to AP. Okay, then we can multiply from both sides of the, so here we have PD, P inverse, this is equal to AP times P inverse, and then P times P inverse, this is equal to the identity matrix again, and then we can say that the A is equal to P D P inverse. Okay, so two essential equations here, they are right here. So the A, it is diagonalized in this way, and also A, as a result, is related to D in such a relationship. Now, let's imagine for a moment, what is A squared? A squared is equal to PDP inverse, such as in here, PDP inverse times PD P inverse, and this is equal to PD P inverse PD P inverse. So these two, if we multiply them, we get the identity matrix. So here we get P D squared P inverse. So this is the A squared. Now, similarly, we can also say that A cubed is equal to P D cubed P inverse. Or we can generalize all this power of matrices as follows. A to the power n is equal to P D to the power n P inverse. Okay? And now, what is the use of using, why do we need to do this? This is a valid question. And regarding this, we know that for any multiplication of two matrices that are n by n, okay, so let's assume we have a matrix A times a matrix B. This is equal to a matrix C. And so this is equal to n by n. And we want to find this element. What is this element equal to? So if we have this is the matrix C. So this specific element here, Ci, j, this is equal to A, I, k times B, k, j. Okay, so this is each element in the resulting matrix. It's equal to the ith row. So we pick here the ith row, okay, and then we pick also the kth. What is this? The jth column. So here we have the jth column, and then we multiply this. How do we do it? Each element in this row, we scan it over times each element. We do a pairwise multiplication of this row with this column. So what we do is that we keep I the same, we keep j the same, and what we are changing the k. So we are moving from this element to this element to this element, and each time the first element is multiplied with the first row. Then, so it looks like the value of k, which is going to change here, k is a number from 1 to n. And in fact, this multiplication, we can, each time we see an index, like in this case k, which is repeated, this means that we are talking about a summation term. So this is the summation of k from 1 to n of A, ik, B, kj. So this is the element that we are trying to find. Now, one question that we can ask here is the following. How many calculations are we doing to obtain this element right here? If we are having n by n matrix.
N plus.
Yes. How many multiplications do we have? The number of multiplications.
Multiplications and one additions.
Okay. So then we have additions. We have n minus 1 additions. So for a single element,
this will be plus n minus.
This is 2n minus 1 calculations for each element. But if we have for n squared elements, because a matrix C n by n, this is n squared elements. So in total, the number of calculations.
It should be n squared multiplying 2n minus 1.
That is true. So this will be equal to n squared times 2n minus 1. So if this is the number of calculations, you can also calculate how much time it takes for a computer to do a specific operation. So let's assume for a moment that we have matrix A if n is equal to 1,000. Now this number, which is 1,000, this is a matrix which is comparable with the images or photos that you take using your cell phone, because cell phones have resolutions in the order of 1 megapixel or up to 20 megapixel. And that one corresponds to an image which has 1,000 rows and 1,000 columns. So we can assume that this is the N, which is the image that you would often take using your cell phone. And then it looks like the question that we can ask is this: if we have matrices A and B, we want to multiply them. The n is 1000. What is time? Which can be measured in seconds. Okay, so this is the question. What is the time to multiply two matrices? So to do this, we can see that the time, which is measured in seconds, is equal to the number of operations, or let me call it calculations, divided by the number of calculations per second. Okay. So if we check the units, the number of calculations, they cancel out, and we can find seconds. So it looks like we are going to get seconds here, which is the correct expression. So what is the number of calculations if we have 10 to the power 3? If we have 10 to the power 3, so this is equal to 2n cubed minus n squared. So this is equal to 2 times 10 to the power 3, all 3, minus 10 to the power 3 to the square, divided by, so a normal computer that we use nowadays, how many calculations can it do in 1 second? What can you say about this? How fast are your computers? So how fast is your processor for the computer you have at home? How many gigahertz is your computer?
3.9 gigahertz.
How much? 2 or 3?
3.9, and then we would have 0.9.
So this means something like 3 times 10 to the power 9. Okay, so this is the gigahertz here. So then this will be equal to, we have 2 times 10 to the power 9 minus 10 to the power 6. And 10 to the power 6 compared to 10 to the power 9 is too small. You can even disregard this one. This is some epsilon. This is infinitesimally small. So we divide this by 3 times 10 to the power 9. So it looks like we're going to get something like 2/3 of a second. Okay? So 0.6 seconds it takes to multiply two matrices. Okay? So it looks like it is some considerable amount of calculations, and it looks like the matrix multiplication, it is an operation which has a complexity of the number of calculations. It is proportional to n cubed. Okay, it changes like a polynomial to the third order. So, and you are good. You can always calculate the necessary number of calculations that is needed. Now, if we diagonalize the system, what are we going to get? So we have a diagonal matrix, which is n by n. So d to the power n, let's not forget, we're trying to write this, right? We said that a to the power n is p d to the power n times p inverse. Then let's see, d to the power n is equal to what? D to the power n, it's equal to lambda 1 to the power n, lambda 2 to the power, n, and lambda n to the power n. So here, lambda 1 to the power n, we have n multiplications. So here we have n multiplications. Then we do this one for n elements, n times n. So here we have n squared complexity. Okay. So what we can get here, an n squared complexity, if we take the a to the power n, we get n cubed complexity. Okay. So then, if we multiply diagonal matrices, how much time would it take? The time that it would take if we have n squared, we would have 10 to the power 3, the size of the diagonal matrix, squared, divided by 3 gigahertz, this is 10 to the power 9, then this will take something like 1/3 of a millisecond. Okay, so it takes approximately 1,000 times faster. So what it would be something between a second or a millisecond. And the millisecond, of course, it's you can do that 1,000 times. So if you want to calculate something at a rate of 100 hertz, so if you want to calculate 100 calculations or input that you have in a system that you are producing, because you will be software engineers, and often you might be required to be very good to predict in a very correct way at what frequency you want to operate, or at what frequency you want to record data. So let's assume for a moment you are going to develop a software and you have to consider frequency of data acquisition. What does this mean? So I want to talk about this. So you need to consider this. The second consideration is you have to consider the frequency of data recording. Frequency of data recording or saving. How fast you are going to save those. Okay. So now let me ask you: has any one of you played with Arduinos, where you could have a humidity sensor or temperature sensor? Anyone has ever done projects like this?
Yeah.
Yes. Okay, that's good. So that sensor, which measures the humidity, if you connect it with your device, you can see the readout right away. Okay. And but this is not the only thing you can measure. You can measure a signal which is changing very fast. You might have an oscillatory behavior which has a frequency in the order of 10 megahertz. 10 megahertz, this is approximately 10 to the power 7 hertz. Okay, so then you're talking about what is, if this is 10 to the power 7 megahertz, this is 100 nanosecond approximately. This is 10 to the power 2 nanosecond, because this is 10 to the power 2 times 10 to the power minus 9. Okay, that's why it is this way. So 10 to the power 2 nanosecond. This is too fast, okay? But let's assume this is too fast, which means that we have to have a system which can record data at a higher pace, a little faster. We can do both examples. We can see here, let's assume that the humidity sensor or the temperature sensor that you are measuring what is the temperature outside, let's assume it's too fast. Then what you can do is that you can have the frequency of data acquisition. This can be 1,000 hertz. This means that you can measure 1,000 times. So each millisecond, you can record the temperature. It's 36.3, 36.3, 36.31, whatever. If something is changing very fast, then what you can do is that you can write a little code where you say that I'm going each 10 readouts, so I'm going to acquire for 10 milliseconds in a row, you are going to acquire the data, you are going to calculate the average, and then you are going to record that one. So that value of the average out of 10 values, you are going to write it down. If you do it this way, you have also removed the noise from your system. Okay, so you can have a 100 hertz data saving. So this corresponds to the second one, and this is the first one. Now, similarly here, if you are in such a system, you need to. Why are we calculating these? We are calculating this because this is how you should start thinking of how much time it takes to add two numbers, how many additions you can do per 1 second, etc. You will see several courses where these calculations, you are going to do them a lot. And one of the most challenging or computationally expensive operations are the matrix multiplication. Another very complex example is calculating the inverse of a matrix. And regarding this, I want to add another example, which is going to be interesting. And I would suggest to you, when you go to your second year, you might work on this problem, or at least by now you have all the information you might need for such an example. The example I want to give to you, that you can think, you can write this one somewhere, and you can work it out later on, is the following. Imagine if you have a matrix which is A, B, C, D. And the question is, what is A inverse? So A inverse is equal to 1 over the determinant here, AB minus BC, times, now this is something which I often forget, but it looks like this is going to be the D here, the A minus B minus C. That's good. Now, you can come up with a matrix which is B, and B is not 2 by 2. Here you can have a 2 by 2, but it can be a matrix which is, let's write numbers 8 by 8. So if and you want to calculate the inverse of the matrix B, in order to calculate the inverse of the matrix B, you can fragmentize it into B1, B2, B3, and B4. Each one of these matrices, they are all 4 by 4, because 4 rows plus 4 rows, it makes 8 columns, so you're good. And now, you can use a similar approach as we did in here to calculate the inverse of this matrix B. So you can play around, you can assume that all of these pieces of matrix B1 and B4, they are like A and D, which you switch places and you can calculate the inverses. Now, so in principle, it looks like often we need to be very attentive into trying to see how many operations we are doing, and this is the reason we want to use the diagonalization. Now let's come up with an example, and the example will follow. Will have the following. So the first application we want to discuss about is the difference equations. Difference equations. Difference equations, what they do, they represent a number of variables which are interdependent with respect to each other. So you can have a variable x, a variable y, and a variable z, and you want to calculate what happens with these values if you do a change on the system, okay? So you update those, and then the subsequent value will depend on the previous values, okay? So you're going to have a recurrence relationships, which is going to look something like this. A vector xt plus 1 is a function of the xt, okay? So this means that at each instant, we have to look at the previous state, and then we get the new state, okay? So this is what we have. As an example, we can assume, for example, let's assume that you have a bacteria or you have a virus. Now, and you want to see how the virus is spreading. Then what we can say is that it could be that we can say that xt plus 1 is equal to a times xt. Okay, so this is the relationship, which could be the following: if a is equal to 2, this means that the virus or let's say the bacteria, it doubles by 2 at each instant. Now, each instant can be 1 second, can be 1 day, can be 2 weeks, or even the spread of a disease, the spread of a pandemic. Let's assume that, unfortunately, if it happens that the number of people that are affected by a disease, the number might double each day, okay? And then this is the equation that one might need to use to predict the spread of a pandemic. So if you have a factor a is equal to 2, let's keep this in mind. This is what this means. And then we can also say the following. So what we have xt plus 1 is equal to a times xt, and this is a times xt minus 1. Okay, you see, so we can continuously multiply by a, but in principle, we can also deduce that xt plus 1 is equal to a to the power t times x0. Okay, so this is the general expression. And let's assume that initially we are starting the system with 3 bacteria. Let's assume that x0 is equal to 3. And then the question is, how many bacteria are we going to have after 4 days? Okay, so given these initial conditions, we can say x4 is equal to what? This is the question. In order to do this, we write the following expression. We say x4 is equal to a to the power 4 times x0. A is equal to 2, so we get 2 to the power 4 times 3. We get 4 times 4, 16, so we get 48. So it looks like one can measure 48 bacteria after 4 days. So these are the different relationships. Now, this is a relatively simple expression because we have only one variable. We have only x. But imagine for a moment if we have two different bacteria that are competing with each other. Okay, so the system is not as simple, but we can have x and y, which can and the x and y can be related such that an increase in y, it might cause a decrease in x. So these are interdependent expressions. And this, a good example regarding these is also, for example, if you assume the number of foxes and the number of rabbits. So the foxes eat the rabbit because they need to feed the little foxes, they need food. But then if they eat too much of the rabbits will die and the foxes will also die because they will have no food. Now this is the type of equations that we can construct. And this also shows that since we can solve this using the principles of linear algebra, these problems that we just discussed, they're very beautiful problems which are very essential, and people that are good at doing numerical analysis or numerical calculations on the spreads of diseases or the spreads of bacteria, people that have this kind of knowledge, they are they're too much required out there. Now, let's come up with an example. Let's assume that we have a variable which depends as follows. Tx plus 1, this is 7xt minus 15 yt. So this means that if the initial condition is xt and yt, then the subsequent value for x, it is 7 times xt minus 15 of yt. And then the other equation, this is yt plus 1, this is equal to 2xt minus 4yt. So here we have a system which is a little more complex than this, okay? Again, a was equal to 2. Let's enter here the 2 in order so that we can observe the similarity. Now, this case where x, it was just a number, this was relatively easy. And also, with the same difficulty level, we can also find the subsequent value, which is not just a number, but it's a vector. The vector that we have to figure out as it is progressing over time, it is going to be a pair of numbers. And we know that a pair of numbers, they constitute a vector, so this should not scare us at all. We shouldn't be afraid of assuming that now we are going to deal with a vector. Now, this statement here, we can reformulate this one as such. Xt plus 1, yt plus 1, this is the vector later in time. This is equal to 7 minus 15, 2, and minus 4. And here we get xt and yt. So this is the reformulation of our problem. And now, since we are discussing the topic of diagonalization, immediately a good student of linear algebra, the first thing that she reports is that, okay, I see a matrix, but it's not diagonalized. So why not diagonalizing this one? Because the off-diagonal terms, they are non-zero. And this is a problem. So we always have to look for these terms, which we write them like this. Off-diagonal terms. And they are non-zero. If they are non-zero, let's try to diagonalize them. Then, let's see also, so in principle, it looks like, let's assume that this is a capital X t plus 1. Apparently, this is equal to a matrix A times capital X t. Okay, vector, vector, matrix. So this is the equation that we are going to deal with. Now, so what we have here, we define the problem, okay? But now, what could be the complete problem that we may need to solve? So, the problems which are relatively difficult and or people that don't know linear algebra find it really difficult, but not us, they will be as follows. First, we define the dependence of the different variables, and then the questions would go like this. So you are given the matrix A, and then you will be given x0, okay, and the question would be find xd. So it's really something given an initial condition, okay, find how it is going to be later on. So if somebody borrows money from a bank, normally the money that you have to give to the bank back, it greatly depends on the amount of money you initially borrow, okay? So you can borrow 10 euros and you pay some amount back. But if you borrow 10,000 euros, of course, the amount of money which you're going to pay back is going to be much higher. So this is the x0. It will greatly depend on the initial conditions. So I need to write this down. So this is the initial condition. So this is a variable which is going to change with time. And we need to find, as a function of time, how this is going to change. And the problem here, then, and let's assume that we start with an x0, 1, 1. Okay, so let's assume we start with an x0, 1, 1, and we immediately, in order to understand this problem, we can formulate it using the schema that we use so often. So this is the standard basis, and the standard basis relationship, it is 7 minus 15, 7 minus 15, 2 and minus 4. So here we have the matrix A, and we want to determine immediately another matrix which is diagonal. And then here we have the x0, which is 1, 1, okay? So this is one variable. And now we want to diagonalize the system. Actually, so the first thing that we should move on is we should find what are the eigenvalues and the eigenvectors. This problem, so what is the steps? The steps will include the following. We have the matrix A, so we do A minus lambda I. This is equal to 7 minus lambda minus 15 to minus 4. Sorry, this is also minus 4 minus lambda. Then we need to write down what is the determinant of this A minus lambda I. And here we have 7 minus lambda times minus 4 minus lambda plus 30. This is equal to 0. Then this is the characteristic polynomial, and this is the characteristic polynomial. This is of the second order in a variable lambda. And this is equal to lambda squared minus 3 lambda plus 2. This is equal to 0. The roots of this characteristic polynomials, so this is the characteristic so we have to look for the roots. The roots of the characteristic polynomial, they are the eigenvalues of the system, and they are 1 and 2. So we can try 1 squared minus 3 plus 2 is 0. So the 1 is satisfied. For the 2, we have 2 squared is 4. 4 minus 6 minus 2 plus 2 is 0. So they are both roots. If they are both roots, that means that the diagonalized version of the matrix A is the following. We have 1, 0, 0, 2. We did it. Okay, so we diagonalized the system. So this is as much as we know. The next question is, can we determine what is the matrix P which enables us to conduct the linear transformation or to project vectors from one basis to the other? So for the moment, this is the question. So what is P? in order to determine the P, we have to find the eigenvectors. And for the first eigenvectors, which is eigenvector which is 1, we have the following: 7 minus 1 minus 15, 2, and minus 4 minus 1. So this is 7 minus 1, this is 6, minus 15, 2, minus 5, times AB, this is equal to 0, 0. The pair of numbers which satisfy this condition, so let me write here, these are the eigenvalues, right? This is eigenvalues. And now, the pair of numbers which satisfy this condition is such that 2a is equal to 5b. So a and b, they can be 5 and 2. So here we get the 5 and 2, and then in a similar way we can find also the other eigenvector, which is going to be 3, 1. So now we have all the necessary information written right on the board, because again, we have here, so these three matrices are essential. P is equal to 5, 2, 3, 1, 5, 2, 3, 1. P inverse.
Minus 1, 3, 2, minus 5.
Let me say minus 1, 3, minus 1, 3.
2 and minus 5.
4 minus 5, okay. So, and then we have also, so let's write this down because we care about these. The diagonalized version of matrix A is a matrix D that we can see here. Now this part, maybe we didn't need to do this one in detail because we have done a few examples, but let this be the next example on the line. And then we need that now to identify what is a to the power m. Now, a to the power n, because the question is, we have to find, using these matrices, we have to find what is the vector x, t, and xt is equal, or a to the power t times x0. To calculate this, we need to find this, and this is equal to p. What is this, p or p inverse? P to the power t, p inverse, and this is equal to, you can see this much on the board. So p, 5, 3 to 1, 5, 3 to 1. The diagonal matrix, this is 1 to the power t. We get 1, 0, 0, 2 to the power t, and multiplied by the p inverse, which is minus 1, 3, minus 1, 3, 2, minus 5. So then we move ahead and we multiply the first two matrices. For the first two matrices, we get 5, 3 times 1, 0. So we multiply the first row with the first column. So we multiply the first row with the first column, and we get 5. Then we get
3, 2 to the power of t.
3, 2 to the power of t.
2. And 2 to the power of t.
2 to the power of t, that's true. And then we have minus 1, 2, 3, minus 5. And this will be equal to, so here we have a 2 by 2 matrix. Here we have a 2 by 2 matrix also. So the answer will be a 2 by 2 construct again. So this is equal to minus 5 plus 6 times 2 to the power of t. So minus 5 plus 6 times 2 to the power of t. Then here we get 15 minus 15 times 2 to the power of t. Minus 2 plus 2 times 2 to the power of t. 6 minus 5. 6 minus 5 times 2 to the power t. Okay, so this is a to the power t. If this is a to the power t, we can try to determine what is the xt in general. Wait a second. So this is going to be.
We can multiply it with 1, 1.
Yeah, that is true. So starting with a given value, we can say that this is equal. Let's do it like this. Let's multiply here with a different color here. 1, 1. Okay? Because if we write this whole expression again, this might take some time. So this xt, this is a 2 by 2 matrix, right? And we multiply it with a 2 by 1. So now we should get 2 rows and a single column. Okay? So then we multiply the first row here with 2 numbers which are 1 and 1, and those 2 numbers will give to us 10 minus 9 times 2 to the power t. This is the first number, and the other number, it is 4 minus 3 times 2 to the power t. Okay? So this is the answer, the general answer of the general solution of our problem. Now, so we can now try to determine what is x4. What was this value x at 4? Then this would be equal to 10 minus 9 times 2 to the power 4, and 4 minus 3 times 2 to the power 4. Then the numbers will give to us 2 to the power 4. It's 2 to the power 4 is 4 times 4, 16. 16 times 9, this is 144. Then minus 134. Minus 134 is the value of x. And then the other value, we get 2 to the power 4, it's 4 times 4, 16, minus 48, minus 44. So here we get minus 44. Now this is x, right? So we started with 1, 1, and we ended up, actually, let me use this a little more. So the initial condition, we start with 1, 1. And a little later, after 4 units of time later, or after 4 iterations, we get minus 134, minus 134, minus 4, 4. Okay, so this is what we obtained. Now, we did this calculation, but one other thing that we can add is the following. What could be these 2 vectors in this other in this basis? Not here, but here. So, or the initial conditions in the standard basis. How are they projected into this basis? This is so how can we find the initial conditions here? What is that? Now, let me ask Joey. Joey, you can write your answer in the comment section. How can we find the initial conditions? So in this basis, it is 1 and 1. But how does this look in the new basis? Okay, I'm waiting an answer from Joey. I thank Ari Decoli for offering to answer, but I want to get an answer from someone else. We have here Joy, or at least I want maybe we can pick up someone else that raised their hands in the comment section. We have here. Irisi. Irisi, can you answer? So let's continue. So it looks like, or you can ask Ari. Ari, can you answer this for us?
Well, we have to multiply with p inverse.
Exactly. So that's true. Because we're saying that given x0, find u0. So we're saying this. We have, wait a second. So we have x0, which is in the standard basis, and we need to find this element. So how do we come backwards? We come with p inverse. So if we multiply x0 with p inverse, we are going to get another vector u0. Okay? Then we have the p inverse, which is right here, and then we find that the u0 as a vector, which is composed of a pair of numbers. This pair of numbers, let them be u and v, okay? Or you can write them v and w, so that we don't get confused seeing the u a couple of times. So that we're not confused, this is something like, this is v and w, a pair of numbers, which is going to be equal to p inverse, which is -1, 2, 3, -1, 2, 3, and -5 times 1, 1. So here we get -3 plus 1. What is this? 2 minus 3. Is this correct? So it looks like the initial condition, looking at the from a different basis, it's equal to not 1 minus 1, but 2 minus 3. So then we can ask the other question. We can say, if this is u0, what is u4? How do we find u4? Which means that, so let me write it here. This is x0, okay? This is x4. Now, using transformation, we found here u0. And now we want to find u4. How can we obtain the u4? The u4 is going to be equal to 1, 0, 0, 2 to the power 4 times u0. Or let me write this one in the formal formulation. So u4, it's equal to d to the power 4 times u0. So it is a similar construct as we did before. D to the power 4, it is 1, 0, 0, 2 to the power 4 times 2 minus 3. Okay? So then this will be equal to, this will be 2. Wait a second. Is it correct? Yes, this is 2. And here we get minus 3 times 2 to the power 4. This is minus, what is this? So 2 to the power 4 is 48 minus 44. Am I right or not? 3 minus 48. 2 to the power 4, it's, yes, this is minus 48. So this is 2 minus 48. Okay, we found this. Now, is there any other way to find x4? To find x4, Ari, any idea? Ari, decoded?
We can multiply once again x4 with p inverse.
No, I'm saying, how can you find x4?
We can multiply the u4 with p.
That's correct. Okay, so this is going to be p times u4, because we just want to transfer now from this domain to the other. So what is p? P is 5, 1, 2, 3 times u4, which is 2 minus 48. And this is equal to 5 times 2, 10, 10 minus 100 and, so this is 48 times 3, this is 144 minus 134, minus 134. And here we have that minus 48 plus 4, this is minus 44. Okay, so it looks like we can solve the problem or the question that we asked. So our question, it was this: given x0, which is this, find xt, or let's say x4. This was the initial question. And then we can, the problem, it looks like it takes less time if we solve this in this domain, in this domain, okay? And you can compare how much effort you spent regarding both, but this is relatively simpler. Do you have any question? But wait a second, can you see, you can see the board, right? Do you? You're not losing much? Okay. Now, calculating eigenvalues, wait a second, so eigenvalues are 1 and 2. So, in principle, it looks like the equations in this domain, they are as follows. We say that xt is equal to a to the power t times x0. Here, we say that ut is equal to d to the power t times u0, okay? So everything, it has its own equivalent. And the equivalence between these principles, they look to be as such. xt, we denote it with ut, okay? x0, in the new domain, it is u0. The matrix A in the new domain is D. So all you need to do is just go and substitute wherever they are. So then, in the initial conditions, often we give them in the standard basis, as in this example here. So if you need to find the xt later, what we can do is the following. The procedure can be this. Given x0, the data, we find u0, and then we find ut, okay, and then we find xt. So this would be a very good procedure. So if you follow from here, this means that you can, from this 1, 1, we go and find this 2 minus 3, and I want to show this one correctly. I think you do remember that what the p does, coeficiente pânul, să lucrăști du trebuie discatieră si fac în. So the schema of how we solve the problem can be the following. Given the initial condition in this domain, we get this, and then in this new domain, we find using from this value, or let me do it like this. We come here, and then from here, we're coming back to the solution we are looking for, okay? So I try to do some clean job anyway. Or, again, we can say that x0, we go to the new domain, u0, we come down to u4, and from u4, we come this way with x4. Now, this is a better drawing because this is, if you are on the right, on the left side, you are on the standard basis. If you are, sorry, if you are on the left side, you are on the standard basis. If you are on the right side, this is the new basis. Maybe this schema, you can read this better. They are all equivalent. As a reminder, this is the standard basis, this is the new basis, and the approach that we can use is here. Okay? Do you have any questions? We have a new individual that wants to join our class from outside the institution, and I'm going to share with you who wants to join us. And let's see, let's admit him. So any further question? If not, we can stop this session and start again later.